Thank you. So, I was excited to be here, and as I was thinking through, as I was preparing for the talk over the last few days, I was trying to think through what might be the most useful things for me to share with you. And I think I realized that in the last few months, or maybe a small number of years, there's been a lot of talk and discussion, almost hype, about AI and deep learning. And what I wanted to do was today share with you what I am seeing in deep learning and in AI, so that by the end of today, I hope that you come away with a very clear-eyed view of what is deep learning, what it is, what it isn't, as well as for those of you that work for various tech companies, I hope that you'll be able to, after today, have the knowledge you need to steer your organization strategically, as deep learning technology has an increasing impact on the technology sector. So deep learning is one of those technologies that, many tech companies are now investing heavily in, is driving a large amount of economic value, and I think it will have a growing impact on a lot of technology. And I think that despite, let's see, trying to figure out, okay. And despite all the hype, or despite all the discussion, I think relatively few of us in academia have come out and made a very clear statement of what it is, what it isn't, what it can do, what it can't do, and so I hope to share that with you today. So deep learning is a broad term that I think encompasses a vision shared by many researchers of building very large-scale simulations of the brain in order to make progress in AI. And is already shipped to many products. Some of the technology in your cell phone today is probably powered by deep learning. And just this morning, I was reading about the new Amazon cell phone and about the Firefly feature, and that sort of thing is powered by machine learning and by the sorts of technologies that deep learning will have a huge impact in. So why do we work on deep learning? Why am I excited about this technology? Let me share with you a little bit of my own history. A few years ago at Stanford University, I was working on robots. And my students and I would try to write software that could program our robots to go around and find our coffee mugs. They say, robot, please find my coffee mug. And we found that when we used the state-of-the-art computer vision techniques to look at these pictures to try to find a coffee mug, it would think that all of those things are coffee mugs. So why is this hard for a computer, right? Well, it's so obvious where the coffee mug is. How on earth could a computer fail to recognize it? It turns out that where you and I see a coffee mug, if you zoom in to a small part of the image, say where that little square is, where you and I see a coffee mug, the computer sees that. And the computer vision problem is to look at all those numbers and tell you that that is the rim of a coffee mug. So for a long time, AI researchers, machine learning researchers like me would say, wow, it looks like a really complicated mathematical problem to look at all those numbers and tell you that that's a coffee mug. So in order to meet the challenge of addressing this complex mathematical problem, let's write really complex mathematical computer programs. And so I would write a program to detect coffee mugs, my friend would write a program to detect cars, that other friend would write a program to detect faces, and there was a sort of proliferation of programs and almost an arms race to see who could make the most, god-awful complex program to do this. And so this is actually 6 screenshots that I took from 6 of the leading computer vision techniques. And the SIFT, S-I-F-T, is actually the most highly cited paper in computer vision for the last 15 years. It is a really complicated computer program that one of my friends wrote over a course of about 10 years. And I guess single most highly cited paper in computer vision. I've actually read the paper about 5 times now, and even today, I really don't understand what it's really doing. So computer vision is hard. What are other things we want our computers to do for us? I think I would like computers to recognize speech. And especially with the rise of mobile phones, I think audio, speech recognition is increasingly important. And just as computer vision is hard, so is speech recognition. The speech recognition problem is for a computer program to look at all the numbers, to look at this waveform, speech waveform, which is patterns of subtle expansions and contractions of air pressure, and to tell you that this graph of air pressures over time represents me saying, robot, please find my coffee mug. So looking at this complex mathematical problem, once again, in academia, there was a proliferation of increasingly complex programs to do different things with audio. You might write a program for speech recognition, someone else might write a program to detect environmental sounds, someone else might write a program to clean up background noise, and so on. And for myself, ever since I was a high school student, ever since I was like 17 years old or something, I always wanted to work on AI. And working at Stanford University, seeing how really complicated this field was going, I actually said, well, others are writing really complex programs, but we're Stanford University, we can write even more complex programs. And we actually did that for some number of years, but frankly, it never really worked. And so for some time, I actually thought that it would be very hard to make progress in AI and perception. That was just too hard. Maybe we should work on other things. Like, let's all just go build spam filters or something else. But about 7 years ago, 6, 7 years ago, I came across one idea that changed my mind, that gave me much more hope that we might be able to make progress in AI within some number of years, or maybe small numbers of decades. And this is that idea, which is that rather than all of us going off and writing increasingly complex programs and writing 50 different computer programs to make the computer do 50 different things, we look to the human brain for inspiration, and there's a fascinating hypothesis, not proven fact, but this fascinating hypothesis that the way the brain does perception is not by having 50 or 100 or 1,000 really complicated programs to do the 50 or 100 or 1,000 things the human brain can do, but this fascinating idea that perhaps most of perception in the brain may be due to one learning algorithm. So what do I mean by one learning algorithm? The human brain does so many things, we do so many things, so what do I mean when I say a lot of this might be one algorithm? So let me share with you some of the evidence for that hypothesis. So it turns out that, shown in this diagram, that red piece of brain tissue shown here is your auditory cortex. You use that red piece of brain tissue in order to hear. Neuroscientists have done the following really cool experiment, a really fascinating experiment, in which it is done in animals, not in humans, but they cut the wire from the ears to the auditory cortex and then rewire the brain so that the signal from the optic nerve, the signal from the eyes, eventually gets routed to the auditory cortex. It turns out if you do this, the auditory cortex learns to see. And this is the word see in every single sense of how I know how to use that word. These animals will do visual discrimination tasks. They can look at pictures and make correct decisions using that red piece of brain tissue. That red piece of brain tissue is your somatosensory cortex. You use it to process your sense of touch. If you do a similar neural rewiring experiment, your somatosensory cortex will learn to see. So there's a surprising amount of evidence that to a surprisingly large extent, not always, but to a surprisingly large extent, the same physical piece of brain tissue can process sight or sound or touch or other things. And if the same physical piece of brain tissue can process sight or sound or touch, then maybe there is just one algorithm that can learn to process sight or sound or touch, depending on what data you feed it. And so starting 6, 7 years ago, my collaborators and students and I started to embark on a quest to try to discover maybe some approximation of this algorithm to see if this might be a better way to make progress in machine perception and to make progress in AI. So how does the brain work, right? Your brain and mine is jam-packed full of neurons, huge number of neurons that communicate with each other, that send little impulses, electrical impulses to each other. All of human learning, all of human thought is made up of these neurons sending electrical impulses to each other. So what we, really a large community of researchers, did was work on what's called neural networks or artificial neural networks, which is software that takes loose inspiration for how we think the brain might work and loosely simulates huge numbers of neurons. And using these sorts of artificial simulations of the brain, we've been able to tackle a number of things. So when we talk about neural networks and deep learning, it turns out that deep learning actually encompasses two separate ideas. And in most of the presentations that guys like me make, we've tended to commingle those two ideas, and I think is sometimes cause the messaging to be confusing about what these algorithms actually do and don't do. So what I'm going to try to do today, really, this is the first time I'm trying to explain this publicly. I was actually preparing this talk until 3 a.m. last night. Jenkin will tell you she saw me drink a lot of coffee this morning. But what I'm going to try to do is share with you my view on really what are the two big ideas and somewhat distinct ideas in deep learning. So the first reason that deep learning works is that it turns out to be very good at learning from tag data. Here's what I mean. Let's say you want to learn to recognize coffee mugs, that robot. What we can do is find a bunch of pictures of coffee mugs, and we'll go to our computer and say that's a coffee mug, and that's a coffee mug, and that's one, and that's one, and that's one, and that's one. And we'll find lots of pictures of coffee mugs and have the software learn from this data what is a coffee mug. And then, the next day when we can test it and say, oh, what do you think that is? And hopefully it'll recognize that that's a coffee mug. So we call this learning from tag data, because we go out and we find a bunch of pictures and we tag the coffee mugs in the data. For those of you that are aficionados, or for those of you that are experts in machine learning, the technical term for this is supervised learning or learning from labeled data, but I'm just going to speak more informally about learning from tag data today. And so it turns out that we as a society, with the increased digitization of our society, with more and more of our activities in the digital realm, we, all of us, are generating previously unimaginable amounts of tag data. And neural networks or deep learning algorithms turn out to be remarkably good at soaking up huge amounts of tag data and making accurate predictions. For this particular problem, we wound up, we actually drove up and down the Bay Area, basically bought every single coffee mug we could find in any store, and we took pictures of them from all orientations, eventually fed about 50,000 pictures of coffee mugs to our software, and in order to build our coffee mug detector. Let me just share with you how well this works. So it turns out, let's see, we're doing this work at Stanford. This is a map of the Stanford Computer Science Gates building. Before we took this sort of approach, we would send our robot around and have it try to find coffee mugs. And before we used this sort of learning massive amounts of data, tag data approach, when our robot went around the offices, it found, every red dot was a mistake that it had found, where it thought it found a coffee mug, but there wasn't actually one. After we did at the end of this project, after driving up and down the Bay Area, getting a lot of coffee mugs, taking pictures, training some of these algorithms up, we had the robot go around again, and it turns out there were 28 coffee mugs in these offices, and it found 28 for 28. Graduate students don't drink quite that much coffee. We added extra coffee mugs into these offices, but there in fact are all the coffee mugs that are found in these offices. So I think that maybe it turns out coffee mugs is one of the objects that's relatively easy for computer vision. There are other problems that are much harder for computer vision, but at least for relatively easy tasks like this, like finding coffee mugs, this technology allowed us to do reasonably well. So after developing the technology to that stage, we're able to find coffee mugs, but not harder objects like cars or do speech recognition or whatever. Some of my Stanford students and I spent some time to examine how can we take the technology to the next stage? How can we improve the performance of the systems further? And in a number of experiments that we ran, that actually Adam Coates at Stanford ran, we realized that there was one very clear trend, which is that the bigger you can build the neural networks, the better it performs. It's that simple. So on this graph, the horizontal axis is how big a neural network can you build, and the vertical axis is performance. And so this trend's very clear. Take any algorithm, if you have lots of data, the bigger you build it, the better it performs. So starting at about 2010, I started wandering around Silicon Valley to try to figure out how can we build bigger and bigger and bigger neural networks. I wandered around to see who had a lot of computers that would, and might let me use them. So it turns out Google has a lot of computers. And so I started, and so I founded and led a project in Google to build out large-scale neural networks and to scale up deep learning algorithms. I was proud that we formed an amazing team there. And so prior to my starting the team at Google, the largest neural networks used in academia were maybe 10 million connections. After the team worked for about a year and a half, we're able to build neural networks with about 1 billion connections, so literally about 100x larger than what was out there before. And since then, by using the scale of these algorithms, the team, I'm no longer at Google, obviously. My old team continues to flourish without me, with which I'm very proud. But we're able to help ship a large number of products. And so perhaps most famously, speech recognition on every Android cell phone in the United States today is powered on top of software that my old team, as well as the speech team, wrote together. And a number of other things. Some things in Street View, image recognition, a whole bunch of other Google products. So I thought that was very successful. But there was another piece of machine learning, AI, deep learning research that I was excited about. So the idea of learning from tag data, it turns out that today, learning from tag data is what drives most of the economic value of deep learning. But there was something about it that always bothered me. First, for some applications, we are running out of tag data. It turns out that no matter how much you drive up and down the Bay Area, you can't actually buy that many coffee mugs. Most stores may have 5 or 10 different styles of coffee mugs. It turns out the best place to buy lots of different coffee mugs is Goodwill. You can go into Goodwill, and for about $1 each, get about 100 different coffee mugs. So it's interesting. I just know stuff like this. Totally useless facts, right? But you know, and also, if any of you have children, if you want to teach your child what a coffee mug is, we showed our computer about 50,000 pictures of coffee mugs, but I can guarantee that no parent, no matter how loving or patient, will point out 50,000 different coffee mugs to their children. So neuroscientists think that the way most of us learn, the way most animals and children learn, is not by having parents tag 50,000 objects for us. Instead, most children learn by going, or animals learn, by going into the environment and just experiencing the world for ourselves. And so the question we asked was, is it possible to have computers learn in a way that is maybe more reminiscent of how humans, how animals and humans learn? And the idea of learning from untagged data. Again, for the machine learning experts, the technical term is unsupervised learning. But less formally, the idea is, can we have a computer go out and just look at a lot of pictures? Maybe look at videos online, look at pictures out in the world, and learn from that in a way that's more reminiscent to human and animal learning without needing every little thing tagged in the environment. So, turning one last time to biological inspiration, how does the brain process images? It turns out that your brain and mine, the first thing it does when it gets a picture, it looks for lines. Your brain looks for lines, or it looks for edges in an image. So in your brain right now, there is a neuron that is looking out, trying to detect if there's a vertical line or vertical edge, like that shown on the left. And there's a different neuron trying to figure out if there's a vertical line or vertical edge, 45-degree line or 45-degree edge, like that shown on the right. These are called these are sort of neurons in early visual cortical area processing area V1. This is the first thing your brain does when it gets a picture. And we were able to, really building on some very inspiring work by researchers at Berkeley, we're able to develop neural networks that could replicate some of these properties of early visual processing. So here are some edge detectors, 16 neurons from the visual cortex of an animal. By training a neural network on untagged data, we were able to have a neural network learn remarkably similar edge detectors. More interestingly, we're able to develop neural network algorithms that not only can replicate early visual processing, our algorithms could be applied to early auditory processing as well. I got this picture from Evan Smith, who does part of his thesis work at Carnegie Mellon. But it turns out that if you apply the same algorithm, not just to vision but to audio, you find that the algorithm learns to listen out for snippets of sound like these. And if you find the closest matches in biology, shown overlaid in red, the software, the same software algorithm, which can mimic early visual processing, edge detection, can also mimic early auditory processing. It learns to listen out for snippets of sound similar to what animal brains are known to listen out for. So the same piece of software can process sight or sound. And it turns out also touch, depending on what data you give it. So one thing we're interested in was previously these algorithms have been run only at fairly small scale, and with our ability to build much bigger neural networks, we were wondering if we could take our little simulated baby brain and have it learn more interesting things than just lines and little snippets of sound. So we ran the following experiments. Hock Ler, one of my good friends, and I and the team ran this experiment. We took a little simulated baby brain, and we had it wake up, so it woke up not knowing anything, and then we had it watch YouTube for a week. At the end of that week, we then probed this little simulated neural network in order to figure out what it would learn. We had a hypothesis that it will learn to detect commonly occurring objects in YouTube. So we know that faces occur commonly in YouTube, and we looked, and lo and behold, it had found a neuron that detects human faces. So what else occurs commonly in YouTube? Right. Cats. And we looked, and lo and behold, we found a different neuron that had learned to detect cats. And the remarkable thing about this was no one had ever told it what a cat is. No one had tagged a single cat in the data. It had discovered the concept of a cat by itself. So I thought this was a promising, maybe small milestone for AI, for machine learning, where the algorithms could discover things in the world by themselves. After publishing that work, I had a bunch of pretty interesting experiences. I would go around and give talks about this. At the end of those talks, I would often have usually a grad student come up to me and say, wow, this cat result is really cool, but I read your paper and I saw you use 16,000 CPU cores to do that, to build these massive neural networks. And then I'll actually get these slightly depressed looking grad students that would ask me like, well, what if I don't have 16,000 CPUs? Am I even allowed to make progress on deep learning? So because of that, I wound up stepping away from my Google role and spending some time with a number of people at Stanford, Adam Coates, many others at Stanford, in order to develop, try to democratize more of deep learning technology. And what we found was that GPU technology, there's a piece of hardware that's already in your computer that's being used to do computer graphics. And it turns out that if you use that piece of hardware to build neural networks, you can very inexpensively build very large neural networks. It turns out to be a much more suitable piece of hardware for building GPUs than traditional CPUs. So Adam Coates, Brian Catanzaro, others on the team were able to, in a fairly short order, using about $100,000 worth of hardware, build even vastly larger neural networks. And with this technology, we're now using it to drive improved performance on a number of computer vision, speech, and other applications. So in terms of, let me share with you a little bit about what I think in terms of the future of deep learning. So there's been a fair amount of mystique about neural networks and deep learning, and most of the economic value for deep learning so far has been driven by its ability to learn from tag data. And it turns out that most learning algorithms, as you feed it more and more data, its performance flattens out after a while. It just doesn't know what to do with all that data. These neural networks are one technology where as you keep feeding it more and more data, its performance just keeps getting better and better. And I think that big data is a confluence of two trends, of the increased digitalization of a society, so we have more and more data because activities in the digital realm generate data, and rapid reduction in storage costs and computation costs. It lets us store and compute on this data. And so to the extent that you believe these two trends will continue, I think that we'll have more and more data in the future. And so extrapolating in the future, I'm optimistic that deep learning will become increasingly powerful for these sorts of applications. And so there's a number of applications where we have a lot of tag data, such as these up here. For some of these, Baidu and other organizations has already made substantial advances, but I predict that these are examples of problems where because of the volume of tag data we have, deep learning in the next 2 or 3 years will continue to make substantial progress. But looking further out, I remain excited about the second portion of AI as well, which is the ability to learn from untagged data. I think this is important because A, for many applications, we just don't have enough tagged data, and B, this is really more human-like. The downside is this is much harder. We really don't know what are the right algorithms for learning from untagged data. It will be a struggle to figure out these algorithms. But I think that for the next phase of AI, for the next phase of machine learning, it will be important for us to try to figure some of this out. Because I think we actually have vastly more untagged data than even tagged data today. So just to wrap up. You know, those of you that know what I get up to know that I tend to build very mission-oriented organizations. When about 3 years ago, my students and I launched the first MOOC out of Standford, and later I invited one of my friends to join me to start Coursera. We had a mission of giving everyone a great education. More recently, I decided to spend the next period of my life pursuing the mission of advancing AI research, to build the hard AI technologies that will allow us to benefit hundreds of millions of users. And after doing a fair amount of due diligence, looking around the valley and so on, I felt strongly that Baidu would be the best place to rapidly advance AI research. And there are a few reasons for that. One is that AI today, sadly, maybe, is a capital-intensive business. You need the data and the compute resources to do that. And so fortunately, Baidu has that. Second, Baidu is an incredibly nimble organization, and tell stories about that. But getting to know the organization has remarkable ability to be nimble and rapidly flow resources shockingly rapidly into where it's most needed. And finally, as I got to know Robin Lee, got to know Alex Cheng, who heads the engineering office here, it's my sister organization and mine, and Yukai Zhang Tong, the other researchers in the US and in China, I was just amazed by the people I met, how nice they are, how nimble they are, how hardworking they are, how smart they are, and I felt privileged when they were willing to let me join them to collaborate with them. So what are we up to? I think that heading up Baidu Research, I know that the next set of ideas for deep learning won't come from me. And so what we are focused on is building the next generation of tooling and infrastructure to enable the researchers working with us to iterate like crazy, to enable the researchers working with us to rapidly generate and test ideas and learn, to have the team come up with the next big set of ideas for deep learning from tagged data and from untagged data. And because of that, what I hope to do is really to let the people working with us be the next generation of superheroes of deep learning. Because of that, we invest a lot as well in employee development, so that when someone joins us at Baidu Research, I want to help them very quickly acquire the superpower of deep learning so that they can rapidly advance to the edge of what is known and then help us push the field beyond that. I started at Baidu just about a month ago. The reason we're in Silicon Valley is because we want to be in Silicon Valley, and we would like to participate in a conversation with the community, to learn from all of you, but also to share some of what we learned back with all of you. And so I hope that this will only be the start to the conversation between Baidu Research here in our Silicon Valley office, as well as all of you. So with that, let me say thank you all very much.